Hey, thanks for joining me. We're going to be going through the rest of this section 1.6 on the rules of inference. And I feel the need to redo this particular problem because I didn't really give you a good example of what you're supposed to do. I mean, it's all correct, but it was just so rushed. So I'm going to start fresh. We'll leave these simple statements over here. Those are fine. And I've grabbed the rules of inference from the book. So let's see, can I just copy this? Duplicate, is that what that is? I don't know. Paste? Yeah, there we go. So that we can refer to the rules of inference and they aren't blurry. So here's how this is going to work. We're going to want to identify exactly what's going on and in terms of what rules we're going to be using. And so what I'm going to do is I'm going to number each of my statements. So we start with number 1. If the baby will fall asleep only if I play music. So if I play music, then let's see, if the baby fell asleep, then I played music. Okay, so baby, then music. Yeah, that's that weird verbiage. Anyway, so that's statement 1. Premise 1. That's a premise, so I guess we could write that. Premise. And someone is going to ask, I'm sure, do I have to write all this stuff? And the answer is, if you want to get a perfect score, yes. So number 2, if the baby doesn't fall asleep, so there's no sleep, where is it? Not B, then I walk the dog. Dog, D. Number 3 is the premise, if I walk the dog, then I get bit by a copperhead. It's another premise. Now, it would be helpful to just bear in mind the conclusion. So I'm going to write it down here. The conclusion is, therefore, if I don't play music, no music, then I get bit by a copperhead. Okay, so we're going to go through and take care of these. The first thing I'm going to do is, if I can remember how I did this before. So we have the premise, if the baby falls asleep, then I play music, and we are going to, I know, that's right. We're going to be writing the contrapositive. So number 4, so notice that I'm going to label each of my items here. Maybe I'll change colors. Yeah, let's do this. Change colors just so that we can be, so those are premises. And then this is the negation of M, arrow, negation of B. And that is the contrapositive. So where do I find that? Well, I guess I didn't grab that from the book, but there was that list of, here, let's see, can I grab it? Sure. Okay, there we have them. So you have all of those equivalencies, and one of them was the contrapositive in particular. It was, let's see, PROQ, that's one right there. So if you didn't want to, you can call it just logical equivalence to the conditional, but you need to label it something. What are you doing here? Okay, now, here's where things get fun. On Friday, I combined 2 steps, and I'm going to separate them into one step. And so this is going to be the hypothetical syllogism. So that's this right here, that hypothetical syllogism that says that P arrow Q, Q arrow R, then P arrow R. So I can only combine two at a time, essentially. So we have 4. Oh, wait. So not M arrow D. And so this is a hypothetical syllogism for numbers 2 and 4. So notice I'm going to refer back to the lines that I just did, and then I'm going to do the same thing, another hypothetical syllogism, not M arrow C, which is the hypothetical syllogism using numbers 5, and 3. And that's the conclusion. And so QED, if you want to use that, or a little box, whatever you want. But that was notice that was the conclusion we're looking for. So the important thing here, though, is that you are putting your reasons down. So reason and your steps. So keep a table of the reasons that you're using. All right, let's move on. We'll bring this back into it as we need it, but right now, I guess I'll just leave that there. Let's take a look at this particular argument if the Democratic candidate doesn't appeal to Latino voters. So let's see. We'll say this is D, is Dim appeals. And then W is Dim wins, if you don't mind me doing it that way. Okay, so if the Democratic candidate does not appeal to Latino voters, then they will not win the election. The Democratic candidate did not win the election, and so therefore the Democratic candidate did not appeal to Latino voters. Does that sound valid? Sounds pretty good. Let me write it again, but just in a little bit more concise form. Therefore, not D. So this is not a valid. You won't find this structure in the rules of inference here. So this the one that's closest to it is modus tollens, but this is not modus tollens. Notice that what you're doing is you're affirming this affirming the conclusion. Yeah, that's what this is called. It's a fallacy. So it's a fallacy called affirming the conclusion. And it is not valid. So a fallacy is just an argument that's not valid. In particular, if you think about it, what this is saying is that if the Democrat doesn't appeal to the Latino voters, then they will not win the election. But it doesn't say what happens. It doesn't say if they do appeal. If they do appeal to the Latino voters, they might or might not win the election. There's other reasons why they might lose, not just because they didn't appeal to the Latino voters. So that's not a valid conclusion. So that's affirming the conclusion. How about this particular? Tomato plants will produce tomatoes only if they get enough sunlight. So if, let's see, we'll call this T is tomatoes, and S is sunlight. So the first statement is, if they produce tomatoes, then they got sunlight. This is one of those crazy English inversion situations. The tomato plants did not produce tomatoes. Therefore, they did not get enough sunlight. This is another one of these arguments that sounds good on the surface, but it's not listed in here. It might look a little bit like modus ponens, but it is not one of the standard rules of inference. In particular, the problem here is that So this is denying the hypothesis. So it's a similar situation to the one above. If t is not true, so t implies s, and if t is not true, we don't know anything about s. We can't say. It could be that the tomatoes, that there's other ways that the tomatoes could fail, not just by not getting sunlight. So this is also a fallacy. Oops. Yeah. Okay, so we're going to move on to dealing with quantified statements. And let's see, did I put the, yes, I have it. Yeah, I have, is this it? Yeah. Sorry, I just wanted to make sure that I have here's the blurry version is under here. That's not that blurry. This one's a little more crisp. Oh, yeah, that's right. I wanted to point out, this is found on page 76 of your book. And then this one, the one that we're about to go over, is found on page 80. All right, let's take a look at this. All perfect square numbers have an odd number of distinct factors. Okay, so for all numbers, for all x, so let's just say that x is an integer. It sounds like we're dealing with integers here. Okay, so for every integer, if it's a square number, perfect square numbers have an odd number of distinct factors. I wish it just said square. I don't like the word perfect there, but for all integers, if you are a square number, so let's do this. S of x is equal to x is a perfect square. And what is the other one? Distinct, odd number of distinct factors. So we'll do f of x is odd number of distinct factors. Okay, for all x, if it is a perfect square, then it will have an odd number of distinct factors. So that's the first piece of this argument. Make this a little bit smaller. So that's number one. Number two is that the number 25 is a perfect square. And then the conclusion is that 25, f of 25. So that seems reasonable. It feels very similar to modus tollens. Make sure I get that right. Ponens, sorry. Yeah, modus ponens. I don't know my Latin. It's been too many years. So it feels like a reasonable argument. Let's look at a couple more of these. The number 2 is a prime number that is even. Okay, so here we are. Let's see. P of x is prime. E of x is even. And so here we have this, let's see. P of 2 and E of 2. So this is what we know. That's statement 1. The conclusion is that, therefore, all prime numbers are even for all x. If P of x, then E of x. I think you probably know or can figure out that that's not a true statement. Or rather, that's not a valid argument. We'll talk about that in a bit. Finally, the number of 2 is a prime number that is even. So we've got the same letters up there. And then therefore, so then that's that. And then therefore, there exists a number that is prime and even. So anyway, So that one feels more like, so this one, this is a valid argument. This is not valid. And this one's valid. Let's talk about why. Okay, so down here, these are the rules of inference for quantified statements. And so you can see that the first one says for all x, p of x is true. Therefore, p of c is true. What that's saying is, well, if this statement is true for all values of x, then it certainly is true for a specific value. So this is called universal instantiation. It just means that if you have a statement that's true for everybody, then it's going to be true for a specific individual. Universal generalization is, it feels like these mean the same thing, but there will be times when we will be able to show that P of C is true for some arbitrary value of C. So that there you've got this statement that's true for an arbitrary value, so therefore it will be true for every value. So that's universal generalization. And then you have existential instantiation, which says that if there exists a P of x, an x that is true for P of x, and so therefore P of C for some element C, and then this existential generalization is kind of the opposite of, it feels like the opposite of that. So from above here, what's the deal here? I don't know that that's, yeah. This is just modus ponens, sorry. Keep getting those mixed up. Although I suppose that in particular, that if this thing is true for all values of x, then it will be true for 25, the number 25. So you would have to use the universal instantiation for that one. So something is true for every value, then it'll be true for the value 25. Then you can go on and prove the rest of that. This is just a sort of a counterexample that you can't do some sort of a universal generalization with a for every. And then this last one is a good example of existential generalization. So let's go ahead and see how these work. So all movies produced by the Coen brothers are wonderful. So for all x, if it is a Coen brother movie, so this will be C of x, if you don't mind me, then it is wonderful. I don't know that that's true, but we'll go with it. Because premises, we're just going to assume that they're true. The Coen brothers produced a movie with John Goodman in it. Okay, so we're going to say that that is G of x is a movie has John Goodman in it. So number 2, there exists a movie that the Coen brothers produced and has John Goodman in it. Therefore, there is a movie with John Goodman in it that is wonderful. All right, well, let's see if this, if we can prove that this is true. Let's see. So first off, with the, here we are. Let's go with this. Let's start with number 2. Number 2 and existential. Let's see. C of C. I don't like having so many C's around. Well, you call M. And G of M. And this is going to be existential instantiation. Isn't that what it's called? Let's see. Existential instantiation. So existential instantiation with number 2. Sorry, I should call this number 3. So we have number 1, 2, 3. The conclusion is the very last thing that we'll have written down. So notice all I'm saying is that since you have number 2 there exists a movie. Let's name that movie. We'll name it M. So we're going to name it M. Now, number 4 is that since this thing is true for all values, this is number 1, we're going to do universal instantiation with number 1. And so this M, this movie that happens to have the Goodman in it and the Coen brothers, this will be true for it, that C of M, then W of M. Now that we've got that, gotten rid of the quantifiers, we can go back to the this original list of rules of inference back here and use them to prove this, and then we'll go back and try to get this. So my goal here is to get G of M and W of M. Okay, so first off, we have I can't remember all the names of these. So here, let's grab this table, copy it, and we'll paste it down here. That way we'll have it sitting right here where we can see it. Lots of stuff came with it. There, I'll just get rid of the extra ink. All right, so there's my table. And so the first thing I'm going to do is I'm going to take that number 3 and I'm going to split it up. So notice that the 3, where is it? 3 is an AND statement. And since it's an AND statement, we know that each of those individuals are true, individual statements. So C of M is true and G of M is true, but we don't really care about G of M for the moment. So C of M is true, and that is called simplification. Okay, number 6. Since 4 and 5 are true, I'm going to be using modus ponens to say that W of M is true. So for this particular movie, this is modus ponens. So that's simplification, sorry, for number 3. Modus ponens with 4 and 5. All right, finally, well, not quite finally, number 7, notice that a G of M is true all by itself, and this is because of simplification of number 3. And so now we can do this, that combine number 6 and 7, W of M and G of M. You see W of M is true, G of M is true, so now I can just say that W of M and G of M is true, and that's called the conjunction there. So conjunction with 6 and 7. Onward, number 9. Now we can use the existential generalization. You see, there is a movie. It's this movie here. Which movie is it? It's movie M, whatever M is. And so, therefore, we can go with this, that there is a movie for which G of X and W of X is true. I suppose I should have written this one backwards. Let's do it like this, G of M and W of M. There it is. And that's existential generalization. And we're done. QED. Whew. How many more do I have here? Oh, just a few more. Good. So let's take a look at this one. Somebody who lives in Chapel Hill has walked to the end of the storm tunnel by root cellar. Everyone who has walked to the end of the storm tunnel by root cellar has walked by the geocache that I hid. Therefore, someone who lives in Chapel Hill has walked by the geocache that I hid. Okay, so let's do this. This first statement, there exists X, and so we have the Chapel Hill statement. Lives in Chapel Hill is going to be C of X. Walked to the end of the storm tunnel by the root cellar is going to be R of X. And walked by the geocache is going to be G of X. So there exists a person who lives in Chapel Hill. Oh, and has walked to the end of the storm tunnel. That's statement 1. Statement 2 is everyone for all X. Everyone who has walked to the end of the storm tunnel, if they've walked to the end of the storm tunnel, then they have walked by the geocache. Therefore, so here's my conclusion that I want to get to. Therefore, there exists someone who lives in Chapel Hill and has walked by the geocache. All right, so let's see if we can put these together. Number 3, I'm going to pick a person, and we'll call this person, I guess I've got C again for Chapel Hill. So person P maybe? So let's see. C of P and R of P for person P. There is a person. We'll name that person. And this is going to be existential instantiation with number 1. And then now that we have that person, we can say that R of P and G of P, arrow G of P, and that is universal instantiation with number 2. Now, number 5, we can start working on this one person. So just to remind you of the logic here, says number 1, there exists a person, and then the number 2 is for everybody. So let's name that person. That person, we can name him Jim or Fred or whatever, it doesn't matter. But you gotta identify that person, and then after you've identified that person, you can apply number 2, because number 2 is true for all people. So you can say, well, for everybody, including that person from number 3. Anyway, now that we've got that, we can say that R of P is true. And I'm going to have a quick reminder here. This is the simplification from that table with number 3. And then number 6, we're going to use modus ponens again. You have G of P is true. And this is modus ponens. And then you can, I guess we have to say C of P, simplification again, with number 5. Finally, we can do the conjunction, C of P and G of P, junction. With 7 and 6. And then finally, there exists a person. Who is it? It's person P. C of X and G of X. And that is existential generalization with number 8. And we're done. QED. All right, almost done. Are these valid or invalid? So all positive integers whose digits add up to 3 are divisible by 3. The digits of the number 52 do not add up to 3. Okay, so for all integers, we'll just say x are integers. If you add up to 3, then you are divisible by 3. So that's number 1. Number 2, the digits of number 52 do not add up to 3. It is not true that the digits of 52 add up to 3. Therefore, it is not true that, divisible by 3. Okay, if all digits integers whose digits add up to 3 are divisible by 3. Okay, so this is not a valid argument, even though you might say, well, the conclusion is true. And the reason is, so this is, what am I doing here? Not valid. So this is denying the hypothesis. So in particular, you could use the universal instantiation to say that A of 52, then D of 52. So that's universal instantiation, but that the arrow's going the wrong direction for this to be a valid argument. So not valid. Okay. Yeah, even though the conclusion is true, it's just not a valid argument. We deal with this with proofs all the time. Is you might have the right conclusion, but the wrong argument. Okay, Xavier likes all sci-fi movies. So for all movies, let's say sci-fi, then Xavier likes it. Here, we'll go with like. Xavier likes Dune. Dune. Therefore, Dune is sci-fi. Dune. Okay, so hopefully you can recognize this to be the fallacy of affirming the conclusion. So we won't go into it, but yeah, so this, it may be true, but once again, it's not a valid argument. And then finally, if n is a real number, okay, so for all n, so we're going to say that here in reals. How about that? For all real numbers, and n is greater than 4, okay, so that means n greater than 4, then n squared is greater than or equal to 16. Then we have the number, let's see, square root of 15 squared is less than 16. Therefore, square root of 15 is less than 4. So this is a valid argument that you're using the contrapositive for. In particular, you would be, if you want to see how this argument plays out, there it is. What you're going to do is you're going to, first of all, use universal instantiation to say that this is the case, that if the square root of 15 is greater than or equal to 4, then the square root of 15 squared will be greater than or equal to 16. So that's universal instantiation. If it's true for all numbers, then it'll be true for the square root of 15. We'll call that statement 3. Then number 4, let's see, yeah, we're going to use the contrapositive. Well, let's just write it first of all. Square root of 15 squared less than 16. That's the opposite, the negation of the conclusion from number 3. So I'm just going to write the contrapositive of 3. Less than 4, so this is contrapositive. And then finally, modus ponens, our favorite, that since we know number 2, so modus ponens 2 implies the conclusion. So this would be 2 implies 5. I guess I'll just write down. Oh yeah, this is with number 4. 4, and we have statement 2. So there it is. There's some more practice here that I don't want to do, but if you want me to do any of this extra practice, please do let me know, and I'll be happy to make another video, but this one has gone way too long already. Thanks for watching to the end, and might as well smash that like button while you're at it.